Haiyan Huang. I'm from the Department of Statistics at UC Berkeley. So welcome to this afternoon session. It's my great pleasure and also honor to introduce this afternoon's keynote speaker, my senior colleague, Professor Bin Yu. So Bin is currently a counselor professor in the Department of Statistics and ECIS at UC Berkeley. And meanwhile, she is a member of the US National Academy of Science. So Bin obtained her bachelor degree in mathematics from Peking University, China in 1984. And she received a master and a doctor degrees in statistics from UC Berkeley in 1987 and 1990, respectively. After graduation, she once spent a few years in the University of Wisconsin at Madison, Yale University, and also the bio labs. Then she came back to Berkeley and joined the faculty in the departments of ECIS and statistics. So she took over as chair of the Department of Statistics at a really difficult time from 2009 to 2012. That is when the California state is under economic crisis, and also when our department and our university were going through a lot of transitions and changes. So that was a critical time for Bin, and Bin was an amazing leader for us at that time, bringing direction and insights to the department and also her colleagues, help the department to go through a lot of difficulties. And other professional leadership roles she took include a founding co-director of the Microsoft Lab and Statistics, co-director of the Microsoft Lab on Statistics and Information Technology at Peking University, China, president of Institute of Mathematical Statistics, fellow of the American Academy of Arts and Science, so just to name a few. So Bin's research focuses on statistics and machine learning theory, methodologies, and algorithms for solving high-dimensional data problems, with applications to genomics, neuroscience, and remote sensing. So her contributions in data science are having a profound impact on both theoretical and applied research in statistics and machine learning. So there are just a lot to talk about Bin, so I want to stop here. But basically today, it's really our great honor to have Bin to talk about some of her recent research and also share her thoughts and the views on data science. Thank you, Bin.
Well, thank you, Haiyan, for inviting me, and also a very long and very kind introduction. So here I'd like to report on an ongoing project with my colleagues. I'll introduce them. And I feel like this is a perfect data science project. It has all the important ingredients, which I see part of data science. And also answers a very fundamental question in development biology, is like how organs are formed. So here's the team I work with. And my graduate student, Siqi, has done tons of work. It's kind of the main person on the ground in the trenches. My co-lead biologist from IBL and in Sue Sanicka's lab, and my former postdoc, my current student. And we also work with a team of computer scientists in Andy Yale's institute in Tsinghua, and working with Wei Xu, who is also a former PhD from Berkeley. So it's really a group or team effort. So I'd like to start with kind of my research philosophy, is that one's work should be either useful or beautiful. And beautiful comes from my math background. I still love math, but beautiful math. Being both useful and beautiful is rare, but not impossible. So my idol when I left THC from Berkeley, I went into information theory, was actually very much attracted by Shannon's work on information theory, which is so insightful and so useful. And
his single paper in 1948 established a whole field of information theory. And the fundamental limits he established in the paper was actually used for deep space communication, which basically very much a Gaussian channel to measure practical algorithm to see whether they can push further. And he's also credited for contribution to digital computer and digital circuits design, and for contributing to war efforts in the Second World War. So if you haven't heard of him, I hope you have, and read up on him. And the connection with the talk here, it's actually his PhD thesis at MIT in the 1940s was on using Boolean algebra for Mendelian genetics. So you can see this great mathematician had a really wide-ranging interest and wrote a whole thesis on that. And let me show you, so a lot what I talk about today will be machine learning, or the CS people call, where do I go to play this? How do I play this? I don't see a mouse here. Can I play this? What he called ultimate machine was an idea from Marvin Minsky. You guys by then already read the comment, so kind of gave away. So he built this. It's a machine that's nothing except for turn itself off. So it's not very intelligent, but he also liked a lot of the gadgets he used to ride a unicycle. And one little correction to Haiyan's introduction was that actually I went to Bell Labs after I went to Berkeley and came back. So it's more natural. I should have gone to Bell Lab first. But the connection to my talk today, I just want to make a historical connection that we see now system biology, but in the 40s, people were already doing Mendelian genetics. And what I will talk about today is using spatial information of gene expression data. Artificial intelligence, deep learning, was already there, maybe in the name of cybernetics, in the 40s, or probably earlier. And today, I'm going to use machine learning. I have another talk on deep learning, but not here. And people now, instead of using this ultimate machine, people definitely have domestic robots and things along this AI front. And I really like this project because among all the works I have done, I think this work is the closest. It's now there, kind of being both useful and beautiful. And we use tons of something old called applied statistics, and I coined the new name, data wisdom for data science. So I wrote this blog for this big data website to define this kind of quantitative critical thinking, which I think needs to be emphasized a lot more. We know scaled-out computation, data storage, how to compute, but there's not enough emphasis on, I think, is the essence of applied statistics, which with the new name maybe gets more noticed. So I basically paraphrased the Wikipedia definition for wisdom at the time, but I went back, now it's different. So it's at the time when I wrote this blog. I would define data wisdom as the ability to combine domain, mathematical, and methodological knowledge with experience, understanding, common sense, insight, and good judgment in order to think critically about data and to make decisions based on data. So I think the domain knowledge we talked about, but how a mathematical entity, either in your code or on your paper when you write down X and Y, have any correspondence in reality. And that's a very, very key step. And often we don't think very hard. I realized, I have been teaching statistics for 25 years. Even about 5 years ago, I realized when you write down X as a random variable, it's loads of assumptions. You're assuming a lot of replicability, and we often don't teach in a way that we let the student realize this is a key step, and we just start writing X. And of course, the practitioners would just do that too, right? I basically came from math, very like writing math notations, but what does it mean when you write X? It's a single symbol. It removes a lot of variabilities. So I think that's what I try to push here is all this kind of, I'll call quantitative critical thinking. So in Berkeley, we have this initiative of data science. And we have been championing for data like critical thinking. And the social scientists say that, well, we use critical thinking too. I think it's true. So I'll try to differentiate a little bit from the social science. It's very related. It's called quantitative critical thinking. It's that relate the math, the code, to reality. And that's a very, very important process. When you have that step wrong, everything you derive cannot be trusted. But that's the step. It's not like scalable computing is not useful. It's very, very useful. But if that step is not solid, everything else built on symbols will have problem. And just to advertise something Haiyan and I did, we expanded on that little post to an article called Data Wisdom in Computational Genomics, and try to see it's coming to a screen near you. Hopefully your iPhone screen. And it's a special issue, also advertised for that special issue of Statistics in Biosciences, co-edited by Dean, Lin, and Zhao. So watch out for that. So the Berkeley view of data science, we have actually a committee report. I'll be happy to forward to Haiyan it's a committee the chancellor appointed. Is data science really the remerging of statistical and computational thinking? I will, in the end, give a slide on my IMS presidential address a year ago, now 2 years ago, kind of going back to the history of data science or why statistics and computer science were always together. Was 1890 US Census was predicted to take 13 years to finish. And that drove a statistician called Hallowith to start his called Hallowith tabulation machine. And that machine was using punch cards and using the most recent understanding of electricity to count how many people in this category and that. And he had a company and later merged to IBM. So if you go back that far, 120 years, statistics drove one of the first computing machines. And now we're just coming back together. You cannot imagine data without computing and computing without data. And you have this Venn diagram. Some people say data science is the intersection. Some people say it's a union. I think you can make your choice. I don't think it matters too much. And I see the 4 pillars of data science is domain knowledge, data, and computing. And the data wisdom is hidden in this human team. And the human team really integrate the 3 together through this pretty like arts type of thing, like critical thinking. It's not very precise, but it's a lot of judgment calls. Which data you use, which computing platform you're going to use, who you're going to talk to, which paper you're going to read. That's all pretty holistic, not precise as a programming language. And I think for a good data science team to succeed, you need at least these 3 components. Data wisdom. If you don't have people who can really translate, you can have people who only care about symbols. That's okay. But you need people who will be able to translate reality to the symbols. If you don't have people to do that, your symbols are meaningless. And computing, which emphasizes a lot, right? Statistics, machine learning algorithm, parallel computing, memory communication. And this is probably for the industry people, this is a moot point, is the leadership, interpersonal and communication skill. And I really think we operate now more like a team brain. I think my son a couple of years ago dragged me into a movie. I don't know any of myself, even forgot the name. But it was about 2 kind of pilots through some big giant robots can fuse their brain and operate together. I remember it was in the Hong Kong Bay. I don't remember the name. But I thought that gave me the mentor for to think. It's really, we have fused brain. People, can I tap into a biologist's brain and we have a communication channel that's as if I become a biologist. And I think a lot of breakthrough are going to happen as a team. No single brain, I think, can really solve all the problems. But we need good communication. We need to be able to work together instead of saying that whose field is more important than others. And stability, that's something I've been used and other people too, as a general principle for information extraction. So this earlier Baptiste talk, he was using different labs and really bypass, that was my question, a lot of normalization and standardization question, and he only looked at the stable information he obtained. It's kind of, he's really finding stable conclusions across different labs. It's a one formal data preparation. In this paper was actually a special issue for Bernoulli to celebrate Bernoulli's publication paper, Jacob Bernoulli, the paper on probability 300 years ago. I tried to advocate that statistical stability is a form of reproducibility. And in this talk, in terms of methodology, my group's contribution is based on stability and combined with non-negative matrix factorization. And Bryman's, at least, was the one, probably there were early ones too, to really point it out that a lot of modern statistical methods like model selection is now stable. And there's a recent paper from the ETH group really proposed stability or they call invariance as a way to do causal inference. So I think this is just something quite easy to do, right? You want something accessible and reliable. And with large data, this becomes a lot more feasible. With the computation power, you can at least perturb the data and see what happens. So when I teach applied statistics for clustering, I often feel like, which clustering method do I recommend? Because it depends, and depends on the metric. So I just say that try different reasonable methods and only interpret the part that's stable across different methods. Change the data too. Our framework for this project is really an interactive loop that we want to build the software on Spark, which is an Amplify Berkeley Hadoop 2 platform, which is distributed by Apache, and also Fiji is a bioimaging platform, open source. So we do want to, for the other labs and groups to use our development, not just method, but also software. So we have, that's the main part of the talk, we have this, I will call principal patterns. Decompose the spatial image into parts which are meaningful, and we use very simple things, correlation, spatial networks, and we'll recommend to the lab, and they will do knockout experiments, and we start again. Okay, so it's a whole loop, interactive, iterative, and not just like we stop anywhere. And our goal is not conclusive at the end of our statistical story. It's really suggestive. Try to thin down the possibilities for the biologists to do their experiments. And if I talk to them, they say that, well, a lot of PhDs do biology experiments anyway, but we hope to increase the yield rate. Like if you do some computation, you have a higher success rate than otherwise. That would be our contribution. And we have a name called CISPA. It's really this interaction, right? There are many statistical methodologies could bear on our project. And I was at the MSR, Microsoft Research, over the break, after the break, and discovered somebody there like Poon, Hao Feng Poon already has a very nice natural language processing based, basically information extraction from PubMed to find gene-gene interactions. Right, he does it only for human genes, but it's easy to change it for Drosophila genes. And on the CS side, they have challenges too, which I don't really quite understand. Data, metadata management, data-driven automation, open source. So this is really the Tsinghua team is able to do for us. And they had a summer student working with us and had some demos. It couldn't be possible with, we basically have 3 teams and work together. And this is a slide a little heavy, definitely from Wei Xu. The idea is that can you have cloud-based infrastructure for system biology? And for the scientists, you want the front end relatively to be easy to use, and the back end is what they do. Right? We don't see. You hide it nicely. And they also do computer science research. So here is more like a big overview of how my group and my collaborator do data science. And the data we take advantage of for this talk is the Drosophila data, which had been collected before we start working with them by the Sue Seneca's lab. And it's gene expression. At the embryo, you have not just the intensities, but also the locations. So this is like association by guild. This is a new form of gene expression genomic data. If you see two genes kind of co-vary at this particular locality, they might interact. So that's the idea. It's a very simple idea, and it's high throughput, and not just our data. In some sense, RNA-seq, you don't have spatial information, but you have different conditions. And for zebrafish, very similar data. For fly brain gene expression, similar data, and also for subcellular gene expression. So we know that different cancers have different mechanisms, and you probably have image data now. So image data, I think, is going to become huge for biosciences. And actually, my first apply, I was very theoretical for my PhD, even I was learning a lot from my former advisor, Terry Speed at the time, but I didn't write anything. And my first project getting a little apply was actually image processing. It's wavelet image compression denoising. So I always like image. I'm a very visual person. And somebody summarized, actually was Ben Brown summarized, like, you know, oh, your project have something to do with image. I said, actually, you're right. I never thought it that way. I do remote sensing, it's images. And this is thanks to Ben, and Ben thanks to Hai and Peter, who have been working with him, and also my neuroscience, definitely vision, right? So I love images.